So just trying to adjust the mic because I was just saying my voice is pretty loud, so I don't want to be shouting and deafen you guys. So I'm Christos. I work for GridGain as a solution architect in the EMEA region, and I'll talk to you a little bit about Ignite, what it is, some of the features, and how it fits and works with Spark, or how we can complement Spark, and how we can compare against it. So I'll talk a little bit about GridGain, what it is, the relationship to Ignite, a little bit about the Ignite project, how it started, where it is right now. Talk, like I said, in depth with a few of the kind of important features. It's a short amount of time, and then kind of talk a little bit, like I said, how we compare it and how we can integrate with the Spark and Hadoop ecosystem. Yeah, that rocket right there is awesome. So, Apache Ignite. The first inception of GridGain, we started back in 2007. So what it really was is a compute grid, so the ability to execute kind of distributed computations across a cluster of computers. Fast track that, we built kind of a data grid, which we'll talk a little bit about it and what it is. And then come 2014, we take all our code as GridGain, contribute it to the Apache Software Foundation, we create what is known now as Apache Ignite. What is really cool about Ignite is two things. One, we were the second fastest project to graduate after Spark. So I think about 9 months incubation, and then we're a top level project. So two things about that. Great code base. It means we've matured quite fast, which is because we've been around since 2007 and running production systems since year. And the other kind of cool thing, you can check these statistics, I found them on OpenHub actually, is kind of the growth of the project. Last time I just updated this slide, I had about 60 contributors, I had to change it to 82. So a growing community, a great community with a lot of help and a very responsive kind of support. So like I said, mature code base and very active at the same time. So please do check it out and see for yourself. So what's GridGain? I mean, so after we contributed the code, GridGain chose to be kind of the initial kind of support behind Apache Ignite. So there's kind of two editions, what we call GridGain Enterprise and GridGain Professional. So Professional is just a kind of a wrapper, and we help companies with the open source Ignite version and how they can turn it and move it into production. And the other one is really, again, the open source version with some added value add features like data center replication, added security, and so forth. Some important things that are relevant to the enterprise. But what's most important about it is the GridGain, we are the kind of main company that's providing support for production-grade Ignite deployments. So a couple of use cases. We've had a lot of success, or when we started in kind of the financial services industry, so a lot of kind of transaction use cases, so OLTP kind of workloads. So a lot of kind of use cases include kind of automated trading systems, high frequency trading, real-time reconciliation of trades, real-time evaluation of portfolios, so fraud detection, a lot of stuff that the big banks are kind of running from day to day. We have presence in the online kind of and mobile advertising kind of industry with a kind of some analytical use cases where people choose to read or ingest a lot of kind of analytics or real-time data that's coming in and kind of infer a lot of kind of information from it. We're slowly expanding also in the big data kind of side of things. Like I said, we've mostly seen our cases in the transactional kind of side, but we've seen a lot more traction now in big data, and that's where kind of we're expanding our new verticals. And another kind of important thing that we're moving away from finance is moving into kind of travel and e-commerce. A lot of the kind of the big commerce websites, they want to do stuff like real-time pricing or real-time kind of searching of hotels or travels or different bookings. So in essence, it's really about kind of highly scalable and highly performant applications. That's where we kind of see our use cases mainly. So what is an in-memory data fabric? Because this is what we kind of chose to call ourselves. It's probably a new word. It's been around for a number of years since we've kind of released Ignite. So in essence, it's a collection of in-memory data components that really fundamentally help for one purpose, designing high performance and scalable applications. So all in-memory components, for example, let's take one by one. I'm sure if I look at them individually, they're probably familiar. A data grid. This is just a distributed kind of cache layer. So the ability to load information into memory and be able to query that really, really fast. So you can use it as a simple key value store, or you can use it as an in-memory database with very strong SQL API. Compute grid, traditional. Think about something like Spark, the ability to execute computations across this large cluster. So these jobs can carry their data with them, or they can use in combination the data grid and probe and receive this information and execute it in memory. So we've got a lot of stuff like risk analysis or any sort of kind of grid computing use cases. Then we go into more kind of in depth of the customer components. Probably a familiar one that resonates with you guys is Hadoop Accelerator. So we do have a distribution that you can use, and we'll talk about it later on as we move on to the presentation on how you can speed up your Hadoop cluster or how you can integrate with Spark. We also have an in-memory file system that is you can also run. And generally a service grid where you can deploy highly scalable in-memory services that you can call. So in essence, as you kind of get the picture, it's not a data grid, it's not a compute grid, it's a collection of all these components, heavily tested, well integrated, in a consolidated kind of in-memory compute platform that allow you to do any sort of kind of use cases. So if you look at this diagram, it's pretty simply put, and when we kind of, as I move on to slides, I explain how the two components meet together. But overall, the way I see it is there's a computing layer, or the processing framework. We have the data layer where we can store this data in memory, and then of course we can use some sort of external persistency if we need to store this further out. So let's look at about being in memory. There's one fundamental thing. How do we scale, and how can we be resilient? So let's talk about data storage. So there's two kind of modes. When I'm storing my data in this distributed kind of hash map, there's two modes I can use. A fully replicated cache, which is simply put, all the data is available on all the servers. Lose any of those servers, you still have your data. Great for heavy read use cases, where the memory, when the data can all fit in a single node, for example, and then you can replicate that to increase the capacity of your actual system. So think about when I talked about the travel industry, when we said about searching for a reservation or searching for your next booking. That is a classic kind of read-heavy use case where you can use a fully replicated cache or topology, and as you add new nodes dynamically, you can increase your capacity or the amount of searches you can offer to your users. Now, if you look at on the right-hand side, then you can see a partition cache. This is similar if you're familiar with MongoDB or Cassandra or any other kind of distributed databases or data stores. It's exactly the same thing. So what we choose to do is partition the data and split it over n number of servers. If you see in the example, we can also, or in the diagram, you can see we can specify any number of backups. This specific one is actually showing one-to-one backup. I could specify more than one. What this means is if I remove any server or any JVM that you see from that diagram, you would still have all your data. Your backups or backup keys would always reside on different servers than your primaries. And like I said, you can always increase the number of backups. For example, if we had two, in that case, we had increased redundancy. If we remove two servers, I still have my data. 2 points that are important there. You can have also a near cache. So not only keep it on the server cluster, but if you're running a client, you can bring the data closer to the client. Any changes that you're doing in this near cache are actually reflected into the main store that you're keeping on your server nodes. And the kind of last bit that I want to say on this kind of diagram is how we actually scale in real time. So what you can do right here is actually add any node on demand, and then automatically we'll repartition the cluster. So we'll migrate some of the primary keys and some of the backup keys onto this new server. So now we've rebalanced the cluster in real time. Now, what is important there is that you can choose to be eventually consistent or fully consistent. And I think this is one of the strong points that Ignite brings to the table, is its data consistency. We do not come from an eventually consistent background, but more from full transaction consistency, and then we loosen it up as it's required. So, for example, if I required full transaction consistency, you can block any operations on the cluster until the rebalancing is complete. If you don't mind and you can go with more performance and be eventually consistent, then you can just do it only on primary sync. And this way, we won't block any operations onto the cluster, and you will be highly available. So the availability will be there, but it will be eventually consistent. So what's important, I talked about horizontal scalability. So how can I scale out and how can I scale back in? What's important is, as a kind of JVM product, we also kind of support off-heap storage. So what does that give us is the ability to go beyond the kind of limitation of the JVM heap size. Now, what that means, I've seen, some quite crazy heap sizes. I think the maximum I've seen that it was working with a standard JVM is about 30 gigs. Anything beyond that is kind of problematic. But in essence, when you want to use your full kind of server and vertical scale, then it's important to be able to use all this memory. So out of box, what we're kind of offering right now is you have your own heap storage, and you can configure how much you can go to off-heap. And right now, with the new version of Ignite, we're actually preferring to have off-heap storage as the main kind of implementation there. What's interesting, but that's kind of to note, it comes with the GridGain Enterprise, is we all have a local restartable store. So remember, we are running in memory. We can restart the server. We can bring it back from an external persistency store. But what's possible there is actually to keep a snapshot of the data on disk for each node. So remember, distributed kind of topology, each node, when they start up, can load its portion of data, and then they all synchronize. So rather than going from a centralized point and then loading all these nodes, you can do it in parallel. So very, very fast load up and startup time, and very important. So let's talk a little bit about the data grid and how you can access that and the different APIs. So I'll try to keep the presentation simple. It's quite short, and hopefully we get some questions in the end. But in essence, there's two components. It's fully JCache compliant. If you're kind of experiencing this through standard Java, then you can use the simple map API, and you can do your puts, gets, get-alls, and so forth. You can have collocated processing, meaning when an entry hits the server or is inserted, it can trigger a function or a method that can transform this object or this value into something. And of course, you can have events and metrics. So any operation that's occurring in the grid, from inserting data to removing data to rebalancing, anything that's actually triggering, you will get events for that, and which you can query later on to see what's happening in your cluster. So based on the kind of JCache or JSR specification, Ignite builds on top of that. And like we said, we add the fault tolerance and scalability across our cluster. Full key value store. Like I said, you can access them by key. But what's mostly important is this bit here, the SQL queries. A very, very strong feature that comes with Ignite. It's full ANSI 99 compliant SQL querying capabilities. So if you've got an application that's already using SQL, it's very easy to kind of test it and see the benefits. You plug it into your external database, and you just offload some of the tables into memory and try your query. And again, not only SQL queries, but I would say the two most important points are the SQL API and the ACID transaction. So very, very strong data consistency when we come there. And of course, with the SQL come the in-memory indexes. So in any kind of model or entity that you're creating and you're adding into your cache, you can annotate with the relevant fields, indexes, for example, on top of these different properties, and be able to query them much, much faster. And of course, what's important here is actually external database integration. So not only we can keep this data in memory, we can connect as a read and write through to an external database. This can be an RDBMS, NoSQL, or even HDFS or Hadoop cluster. So it's really having the ability to evict any data that's in memory onto disk. And again, the similar scenario, if we were to what is this one? Sorry about that. So yeah, so this, one of the strongest, what you really can do is connect an external database to be able to offload and evict some of your data into this database. Again, it's merely a cache store interface, so we have some out of the box for Cassandra, for MongoDB, for Hadoop, but you're always free to implement your own if you've got your own custom database that you need to connect to. Okay, so briefly I want to talk about the compute grid, because it kind of relates to Spark and how we're going to move to that. So we talked about kind of storing the data and be able to query the data with using different interfaces. What we can actually also do is use tasks or runnables or callables to manipulate the data. And the real essence or the real power, I think, of Ignite is having the ability to move take the processing to the data and not the data to the processing. So it's all about as little data migration as possible. So if I can write a task, take for example, I need to change a certain value of a certain entity or field, increment the salary of a certain employee, hopefully mine. But what you want to do right there, rather than reading the value, changing it, and then writing it, what you want to do is write that change request as a task. Initiate, and what you do, you don't broadcast it to all the servers. You actually use Affinity function or the key of that entity you're trying to modify so that that task executes exactly on the server that has this data. Yeah? If you were using, of course, it's supported out of the box to do kind of standard map reduce operations. So think about a SQL query that we're talking previously. How do we execute that when we're running a partitioned cluster or distributed cluster? What we really do is we map, so we take that SQL query, we execute it on each of the servers, we take the results, and then we reduce it when we present it. So there's a lot of flexibility in terms of how you can process that data and what kind of design, what patterns, processing patterns you can use to do that. Of course, you can always use the traditional approach of moving the data to your processing node. But like we said, the best way to do it is use kind of data locality and be able to process the data as close to the data as possible. What's important about the compute grid, just a few more details. Like I said, there's a direct kind of API for MapReduce. You can do cron-like scheduling, so you can have tasks that are running across the grid for a long time. You can customize the load balancing. Out of the box, we have a kind of a round-robin approach where it just sends to the next kind of server in line. But of course, everything is pluggable in Ignite. So even the way you kind of do the load balancing around for your compute task, you can implement that or change it, and then you can decide how you're doing this load balancing or make an external call. You can do state checkpoints. So because we have the data grid, at any operation when this task is executing at any node on the server, you can create a snapshot of what the state was when you're executing that task. And then if it fails for any scenario, what do? You can resume back from that checkpoint. Because part of your code will be going through, when it reaches the point, it'll check for the different checkpoints and understand in which state it is and resume from there, rather than having to do that all over again. And what's another kind of good feature is not only is the automated failover, so you can design a task to check for specific thresholds, for example, and make it fail automatically. So think a task that requires X amount of CPU power or X amount of memory. You can put that in the task, and if it does not meet certain criteria, for example, it will trigger an exception, which means the task will fail over and then go to the next available server. So the task will still cycle around until it finds the right conditions that you've created for it to execute. And of course, what's really, really, really cool is zero deployment. What that means is after I started my Ignite cluster, I'm writing a class or a new runnable or a new task that I want to execute. I do not need to make the classes available to my cluster before I start it up or to my server. Actually, we have a distributed class loader, so as the client joins the cluster, it can send the task. The classes are loaded on each of the server nodes, and the task is executed anywhere that requires to be executed. If you've got a new version of this task, great, no problem. What happens actually after we execute, we unload that class. So any consecutive same task with a newer version, for example, a new implementation will execute with the new class and not with the old ones. Okay, so now I'll talk a little bit of, hopefully you've gotten kind of a picture of what Ignite is at a high level, what it does. And now I'll talk a little bit about how we fit into the Hadoop and Spark ecosystem. So first of all, two different and similar products at the same time. I think there is places where there's overlapping functionality in terms of Spark, but do we see it as a direct competitor? Not really. I've never seen use case. I've never really been up ahead Spark in the ability to be able to kind of fight against it. So I think in general, we've been more successful with Ignite at looking at OLTP kind of cases. Rather than Spark, where it's more kind of sitting in the analytics space. The full SQL, in-memory SQL support, I guess, is another one that's very, very important. The storage, the ability to actually keep your data in memory and process it, and not having to bring it from somewhere like Hadoop. We're more kind of flexible, how do you say, broader use cases. So whereas kind of Spark is more kind of focused on analytics, and with the kind of Hadoop ecosystem, we're kind of more broad in terms of how we integrate and what kind of use cases we run. Off-heap kind of support, that's another kind of point, again, that you don't get with Spark. But nothing to take away from Spark. It's a great product. It's got a great community, and it's got a great backing behind it. So I think they're both fantastic products, and I think they can both work together really, really nicely. So simply put, what we're actually doing in the integration is giving Spark what we think it doesn't have, which is really that in-memory storage component, the ability to query and bring data in memory. If you look at a traditional kind of Spark use case, you have Spark running on top of HDFS, which then you need to ingest some of this data from HDFS, so you read off disk, you bring it in an immutable RDD in each of the Spark workers, you do your processing, and then that's it, you're off. You get the results and you're done. The problem there is two things. You have to access disk, which is slow, and you can use SQL again, which could be much slower if you don't have the right kind of indexes. And the other thing you can't do is you cannot share this RDDs across Spark workers when you're doing traditionally, since each one just have their immutable data set. With the IgniteRDD, so we're using exactly the same interface. So really, what happens here, if I go back to the data grid, we create a cache where we store our data or our objects that we want to access. And then through Spark, we take the Spark context, we create the IgniteRDD, and then through Spark, we can access that. Now, the point is, because this RDD is hosted separately on the Ignite cluster, then each Spark worker can have the same view of this data set. This is a universal shared RDD that's hosted in Ignite. And of course, you can have more than one. Merely what it means is just another cache or table in your Ignite kind of cluster. And again, since we have a full-blown SQL interface within memory indexes, if you're using Spark SQL, again, that's another way you can speed up the way you read data or you query data and you do your select. So a little bit of code just to show you how easy it is pretty much to get started. And I've got a couple of examples. You can check on GitHub. We can follow up with some links. There's a few easy ones that you can run out of the box. But generally what you do is you start with your Spark context, and then using that Spark context, we create the Ignite context. And then you can see there we have Ignite configuration. So in there, we can pass the Ignite XML. So if you've got some specific configuration for your cache that you would like to use as you're starting up, then you would pass it there. But you can see what we're really creating there is a cache with two things. It uses integer as key and an integer as value. That's all we're creating right now, and we're storing it in Ignite in a separate cluster. So reading values, again, you call the from cache where it creates the RDD, and then from there, you can collect and you can scan and bring the values. Again, the same with saving values, pretty straightforward. And the last bit here, as you can see, how easy it is to just run a basic SQL query. So once we've created the IgniteRDD, you're just in Spark world. So any kind of typical operation you would be doing in Spark using your RDDs, you can do exactly the same. But again, like I said, this will be a shared RDD. You can rerun an execution. The data will still be there. Data that is changing in Ignite in real time will be reflected in your Spark process, and now it's consuming it. So important, I got a lot of questions around this. Does it work with data frames? Does it work with data frames? Yes. So, I mean, the easiest way I found to figure it out is pretty much just create an IgniteRDD, same example that as previously. Use the SQL context. It's probably an older version. I'm sure if this has been updated right now. And then you just call the create data frame function. And then after that, what we're doing is really registering the temp table, company, for example, in this case. And then we're just able to do any sort of operations like filter, group by, select, anything you would do with a traditional data frame. And these are two important demos. These are actually taken code snippets from the examples that I have on GitHub. So one shows just a standard integration with Spark and using a simple application to create an IgniteRDD and have the ability to query that. And the second one, really, I had a question from one of our kind of prospects or clients, which was, hey, can I join two RDDs? So can I join an IgniteRDD with a standard kind of Spark RDD? So great, yeah, this is exactly what this example does if you check it on GitHub. So basically, we create a standard Spark RDD. Then we create an Ignite RDD with the data. So in this case, it's two companies. I create the employees and the companies. So one is standard Spark RDD, create a DataFrame format, and the other one is an Ignite one. We create a DataFrame from that, and then you just call the join method as you would do with a standard kind of operation. So like I said, I'll follow up with the links, and you're free to check it out your own time. It should be fairly straightforward. And just to clarify how this actually works, as you can see on the diagram, each server, you would host your Spark workers. It would be one-to-one with your kind of Ignite node. So as you're starting a worker, it will start a client that can connect to your Ignite cluster. And again, it is possible to use data locality in these operations to be able to do that. Moving towards the last bits of what I'm trying to say, the presentation is, the last bit is IGFS. So as you have HDFS, we also have the Ignite in-memory file system. So what that does is use the same protocol as HDFS. You can see there. So you can either use it standalone on its own, or you can actually use it as a read and write through with HDFS. So you can offload some files that are kept on HDFS, you bring them up a layer into memory and be able to query them or get them much faster. And really, what we in essence do as another kind of component is the Hadoop Accelerator. So we use the Ignite kind of compute grid or the client and remove what previously MapReduce 1.0 was doing. We're using the name node. So this is for existing Hadoop kind of deployments. If you're already using this and you're looking for a way to enhance your current MapReduce operations, then it's very simple. You just install Ignite, you configure your Hadoop cluster to go via Ignite as the framework, and then just execute the exact same application you were doing in Hadoop. So in a nutshell, providing very fast kind of SQL, being in memory with the SQL indexes, shared RDDs across the jobs, across the Spark workers, and across the whole cluster, and of course mutable RDD that comes in. Fully compatible with data frames, so free to use that if you will. And if you're just using traditional kind of Hadoop and not working with Spark, then there is a component for you, which is the Hadoop Accelerator, which will help you alleviate some of the kind of performance problems you're having. And just as a last slide, and we've got 2 minutes hopefully to answer one question, is we pretty much can run anywhere. Any infrastructure that we've tested on. There's a Dockerized version of Ignite. We're running on AWS, no problem. You can consume it from the marketplace. We're running on Azure as well. You can consume it from the marketplace. You can find it on there. Google Cloud, Mesos, and Yarn. So it's out there. Check it out. It's an open source project. Be happy to get more of you guys as contributors. Thank you. Yes?
You said that you support the Ignite support asset. How do you ensure? You said that Ignite supports asset transactions, and how do you resolve concurrent modifications?
So there's two, it's a good point. I didn't put these complicated slides in there. There's two ways. You can have optimistic or pessimistic transactions. So one, the pessimistic, we obtain the lock on the read or on the get. So that is locked. No one else can access it. On optimistic transactions, we actually do the operations locally. And when it comes to commit, then we check the versioning. So each entry in the grid is versioned. So as we're going to do the commit at the transaction commit, we'll check if any of these values have changed. In this case, we throw an exception, and it's really the responsibility of the client to try that again. And of course, in that, there's a multiple types of isolation levels that you can use, from read committed to repeatable reads. So it's all there. Whatever you've been used to with the traditional databases, it will be exactly the same.
So basically, it's our responsibility. As a user on the Spark side should ensure that in concurrent drive, I write into different keys.
You mean if you're using transactions? No, well, so you don't throw an exception, but I guess it depends. I don't understand the use case though. How? We can take it offline. You can come to the booth. We're on S4, I think, and let's talk about it there, yeah?
And that's all the time we have for questions. We're going to queue up the next speaker. Thanks.